Problem 5 asks, during which time interval in the velocity graph below does the particle start moving from rest in the positive x direction? The key thing to remember is that on a velocity versus time graph, anything that occurs in the upper half plane shows motion that moves in the positive direction, and everything in the negative half plane shows motion moving in the negative direction. So if we are looking for a time when the particle starts moving in the positive x direction, we need to look for interactions that happen in the top half of the graph. The second clue that's written in the problem statement is that the particle starts moving from rest, which means its velocity is equal to 0. On a velocity versus time graph, the velocity is equal to 0 when the curve crosses the horizontal axis. On this particular graph, that occurs at the point labeled 3 and the point labeled 5. So we're looking for when the object is at rest, so either at 3 or at 5, and starts moving in the positive x direction, meaning in the top part of this graph. That only happens in the interval 5 to 6 because we start from 0 and then move in the top half, which is positive. So the answer for this one is E, time interval 5 to 6. In problem 6, we're given two vectors A and B and asked to use the dot product to find the angle between them. The dot product is given by the formula A dot B is equal to magnitude of vector A multiplied by magnitude of vector B times cosine of the angle between them. We can also calculate the dot product by multiplying like components and adding the results. So on the left-hand side, we could compute the dot product as AX BX plus AY BY, where the first term are the x components of vectors A and B, and the second term are the y components of vectors A and B. The right-hand side requires us to first figure out the magnitude of vector A and vector B, which we can do using the Pythagorean theorem. The magnitude of vector A will be its x component squared plus its y component squared with the square root over both. If we were to put this into a calculator, we would find that it is equal to 17. We can repeat this to find the magnitude for vector B, so we'd have negative 7 squared for its x component and 24 squared for its y component, and this ends up being the square root of 625, which is equal to 25. Returning to our equation for the dot product, we can figure out the left-hand side by multiplying 8 by negative 7 and 15 times 24, and then plug in what we just found for the magnitudes. Put all of this into a calculator to get 304 on the left-hand side and 425 cosine theta on the right-hand side, and then solve for theta using inverse cosine. Making sure our calculator is in degrees rather than radians, if we plug this in, we'd get an answer of 44.3 degrees, which is C. The next three questions are conceptual questions based on the picture of the three trajectories shown. The first asks us to rank the three trajectories according to the initial vertical velocity component. We can see from the picture that all of the three objects start from the same initial height and all reach the same final height. With this information, let's go to the kinematic equations. Question 7 asks about the vertical velocity component, which we can look at using this equation. The strategy is to see which of these quantities are the same across all three trajectories, which are different, and what can that information tell us about our initial vertical velocity in the y direction, which we're trying to solve for. The first thing that's the same is that because all three reach the same final height, this difference, y minus y naught, is going to be the same for all of them. The second thing that's true is because these objects are just moving through the air under the influence of gravity, the acceleration is going to be the same for all three as well, because it's just due to gravity. The third thing that we can see is that at the top of the motion in the vertical direction, the y velocity is going to be the same as well. Namely, it's just going to be 0. So now, if we look at our equation, we have this term is the same for all three, this is the same for all three, and this is the same for all three, which means that the only remaining term, the initial vertical velocity component, has to be the same as well. So if we were to rank the three paths, they would all tie for this metric. The second conceptual question asks us to rank the paths according to the time of flight. Going to a new kinematic equation, we can answer that. But I'm going to already substitute in negative g for the acceleration, because I'm looking at motion in the y direction, because that's what's going to set how long the objects are in the air. Using the same strategy, let's look at what are the same across all three paths. Again, our heights are going to be the same because all objects start from the ground and all objects end at the ground. So these two terms are going to be the same because all objects start and end at the ground. We had just said that v naught y is the same for all of them. And then t is what we're trying to solve for. The only other thing in the equation is a 1/2, which is a constant, and g, which is obviously going to be the same for all of the trajectories. Again, we have everything here being the same across all three paths, which means that the time the object is in the air must be the same for all paths again. So they tie. The last conceptual question asks us to consider motion in the horizontal direction. For projectile motion in the horizontal direction, the distance traveled is equal to the initial x velocity multiplied by time, and that's it because gravity only acts in the vertical direction. We just said that all of our objects spend the exact same time in the air, so that's going to be the same across all three. V naught x is what we're trying to figure out, and based on our picture, we can see that 3 travels the furthest, followed by 2, followed by 1. If t is the same for all of these, but 3 goes the farthest, that means that 3's initial x velocity must be the biggest. Similarly, if the object 1 travels the least amount of distance, but it stays in the air the same exact amount of time, it must have the smallest x velocity. And so for the ranking for this one, it will be 3, 2, and 1, which is A.